Imagine you're strapped into a spacecraft, watching Earth shrink behind you. Blue oceans, white clouds, everything you've ever known getting smaller. You're heading toward the sun, not into it, but close, closer than any human has ever traveled. Your destination is Mercury, the first planet. Mercury is a trap, and once you go there, the universe itself conspires to make sure you never come back. Most people assume Mercury is an easy target. It's small, it's nearby, it doesn't have the crushing atmosphere of Venus or the distance problem of Saturn. What they don't realize is that Mercury combines every dangerous element of deep space travel into one merciless package. The proximity to the sun doesn't make it easier to reach, it makes it nearly impossible to leave. But reaching Mercury is only the first problem. Surviving it is another. Let's start with the journey itself, because the distance to Mercury is one of the most misunderstood facts in astronomy. Mercury sits roughly 77 million kilometers from Earth at its closest approach. That sounds manageable. Mars is 55 million kilometers away, and we're already planning missions there. Mercury should be simpler, but it isn't, not even close. Going to Mercury is like trying to brake while falling down a mountain. Because of its orbital position near the sun, reaching Mercury requires you to shed an enormous amount of velocity, not at it. The sun's gravity is pulling everything toward it constantly. Your spacecraft naturally wants to accelerate sunward. To actually enter Mercury's orbit rather than flying past it or plunging into the sun, you need to fire your engines against your own momentum repeatedly. This makes Mercury one of the most fuel-expensive destinations in the entire solar system, more expensive than Jupiter, more expensive than Saturn in terms of energy required per kilogram of spacecraft. NASA's Messenger probe, the first spacecraft to orbit Mercury, launched in 2004. It didn't arrive until 2011. 7 years to reach a planet that appears close. And that was an unmanned probe weighing a tiny fraction of what a human mission would require. It performed 6 planetary flybys just to bleed off enough speed to achieve orbit. A crewed mission carrying life support, food, water, medical equipment, and return fuel would be orders of magnitude heavier. The fuel math becomes catastrophic before you even leave Earth's atmosphere. But let's say we solve the propulsion problem. Now the real nightmare begins, because Mercury itself is trying to kill you from the moment you arrive, and it does it in ways that stack on top of each other with no relief. Start with temperature. Mercury has almost no atmosphere. Without one, heat cannot be distributed across the surface. One side is hot enough to melt lead, reaching 430 degrees Celsius. The other is colder than Antarctica in the middle of winter, dropping to negative 180 degrees Celsius. That is a swing of 610 degrees between day and night on the same planet. No material we currently have handles that range without catastrophic failure over extended periods. Your spacecraft, your habitat, your suit, everything is being pushed to its absolute physical limits simultaneously. Engineering for that thermal extreme while carrying enough mass for a crewed mission makes the design problem borderline unsolvable with current technology. Then there is the radiation, and this is where Mercury stops being difficult and starts being lethal. Earth has a magnetic field that deflects solar radiation. Mars has almost none, which already concerns scientists planning missions there. Mercury has a magnetic field, but it is extraordinarily weak, only about 1% the strength of Earth's. It provides essentially no protection. You are 77 million kilometers closer to the sun than Earth. Solar wind at Mercury's distance is 10 times more intense than what strikes our atmosphere. Solar flares and coronal mass ejections, which already pose risks to ISS astronauts still within Earth's protective magnetosphere, arrive at Mercury with almost nothing standing between them and your body. And at Mercury's distance, NASA's astronaut radiation limits disappear frighteningly fast. A single major solar flare event would deliver a radiation dose exceeding NASA's lifetime limit in a matter of hours, not years, not months, hours. There is no warning system reliable enough. There is no shelter thick enough. You are exposed continuously to one of the most powerful radiation sources in the solar system at close range with no meaningful protection. Now consider what this does to the human body over the months required for a surface mission. Radiation damage is cumulative. DNA breaks down, cells mutate, the immune system deteriorates, cognitive function degrades as brain tissue absorbs charged particles. Studies on astronauts who spent extended time beyond Earth's magnetosphere already show measurable neurological changes. At Mercury's radiation levels, those changes would be accelerated dramatically. By the time any crew completed even a short surface mission, the biological damage would be severe and largely irreversible. All of this assumes one thing, that you can leave. Because here's the part that makes Mercury a true point of no return: getting home. The same orbital mechanics that make Mercury expensive to reach make it even more expensive to leave. To escape Mercury and return to Earth, you need to accelerate back out of the Sun's gravitational well. You are closer to the Sun on Mercury than at any other planet. That means you need more energy to climb back out than from any other destination in the solar system. All of that return fuel has to be carried with you from Earth, which means you needed even more fuel to carry that fuel on the way there, which means your spacecraft was already so massive that reaching Mercury at all required a miracle of engineering. The rocket equation does not forgive, it compounds. Each stage of the journey demands fuel, and every kilogram of fuel demands more fuel behind it. A round trip to Mercury is not twice the problem of a one-way journey. It is exponentially worse. The mathematics break down so completely that some mission planners have quietly concluded that the first human mission to Mercury may have to be one way by design, not by accident. And even if the fuel problem were solved completely, you still cannot simply leave whenever you want. Mercury's return windows, the specific orbital alignments that make a trajectory back to Earth possible, are extremely narrow. Miss the window, and you wait. On a planet actively cooking you with radiation, with temperatures swinging hundreds of degrees, with consumables already calculated to their absolute minimum. Every additional day on Mercury is additional radiation exposure, additional thermal stress, additional drain on systems that were never built to last longer than planned. The margin for error is essentially zero. Even the ground itself becomes a problem. Mercury's surface is covered in fine, sharp regolith created by billions of years of micrometeorite impacts with no atmosphere to slow them down. This dust is electrostatically charged by constant solar radiation and clings to everything: suits, visors, seals, filters. On the Moon, Apollo astronauts dealt with lunar dust for just days and returned with damaged equipment. Mercury's dust problem is worse because the radiation charging it is 10 times more intense. Over weeks or months, that dust works into every seal, every joint, every filter. Equipment fails. Suit integrity is compromised. The systems keeping you alive begin to degrade from the outside in. Mercury is not one danger. It is every danger at once. The fuel cost makes reaching it nearly impossible. The temperature extremes stress every material to its breaking point. The radiation exposure is continuous, lethal, and unshieldable. The orbital mechanics make leaving harder than arriving. The mission windows are brutally unforgiving, and the environment is actively destroying your equipment every moment you remain. A human who traveled to Mercury would arrive already compromised from the journey. They would land on a surface offering no protection from the nearest star. They would race against radiation exposure, equipment degradation, and a narrow return window with no margin for error. And then they would have to climb back out of the Sun's gravitational well, with a body and a spacecraft both fundamentally damaged by everything that came before. This is not pessimism. It is orbital mechanics, it is thermodynamics, it is biology. None of these laws care about our ambitions. Mercury has orbited the Sun for 4.5 billion years in plain sight. ancient, silent, and hostile in every way that matters for human survival. We have sent robots there and they have returned extraordinary science. But robots don't need to come back on their own terms. Robots don't need air or water or protection from a radiation dose that would end a human life in hours. When you look at Mercury in the night sky, low on the horizon just after sunset, it looks like a quiet, steady point of light. Harmless, reachable, close. But that light is reflected from a surface hot enough to melt metal, bathed in radiation strong enough to end the life, sitting at the bottom of a gravitational valley that demands more energy to escape than almost anywhere else in the solar system. The first planet is not a stepping stone. It is a dead end. And that is why humans may never truly conquer Mercury. If you enjoyed this video, consider subscribing. I'll see you next time.